In this section, we're going to do more Gauss-Jordan elimination. We are just going to do it on different types of systems. Remember when we were looking at graphing and the substitution and the addition method, we saw situations where we had no solution or we had infinitely many solutions. We need to look and see how that may present itself in this particular method. What is going to happen? So that is our goal for this section, inconsistent and dependent systems. We haven't really given those a name before, or we don't really know what those names are, but we have seen these before. A system with no solution is called inconsistent. A system with infinitely many solutions is called dependent. Okay? Solve the system using Gauss-Jordan elimination. Here, our augmented matrix is -3, 6, 12, 1, -2, -4. My first step here would be to switch row 1 and row 2. And I want to do that so that I have that 1 in the top left corner. Then I want a 0 where that -3 is. I get that by doing 3 times row 1 plus row 2 and putting it in row 2, not changing the first equation, the first row. 3 times 1 plus -3 is 0. 3 times -2 is -6 plus 6 is 0. 3 times -4 plus 12 would also be 0. So what just happened here is I got this bottom equation. Remember, it means 0x plus 0y equals 0. So 0 equals 0. That's okay. That's not a contradiction. That's true. No problems there. What that means, if I get truth out of this, is that we have infinitely many solutions. This is a dependent system. Specifically, it has this relationship where x minus 2y equals -4. Sometimes you'll see this as something like, okay, let's solve this for x to say x equals 2y minus 4. We could write that as an ordered pair where y can be anything, but whatever y is, x has to be 2 times that minus 4. That's the relationship between these because that's what x is when you know what y is. Okay? That is a dependent system. Let's try the same thing for this example. 2, -2, 10, -1, 1, 3. You have a couple of options here for how we get this. I think the easiest is probably to just do 1/2 times row 1, because then you can do it in one step and you don't get any fractions there. Not that we completely want to avoid fractions. Oops, we're putting that in row 1. Not that we completely want to avoid fractions, but if we can, we probably should. They're not the worst thing, but they're not the easiest thing to work with either. Integers are much easier. Now, let's add row 1 and row 2 and put it in row 2 to give me the 0 that I want. 0, 0, wait a minute. I'm not used to both, for everything on the left side of that vertical bar being 0, right? Well, let's think about what this means. 0x plus 0y equals 8. 0 equals 8. No, it doesn't. This is a contradiction. So we get no solution or an inconsistent system. Consistent just means it has a solution. That may mean a single unique solution, or this up here would be a consistent system because it has solutions. It's not inconsistent. This down here is an inconsistent system because it has no solutions. Let's try this one, see what we get here. 1, 1, negative 3, 4. 6, 1, 1, 8, negative 5, 0, negative 4, negative 2. Be very careful with that last row. Make sure you're always remembering this is X, this is Y, this is Z. We don't have a Y, so we have to put a 0 there. I like the 1 in my top left. I am going to work to get the 6 and the negative 5 to be zeros. 6 being 0, I'm going to get that by doing negative 6 times row 1 plus row 2 and putting it in row 2. I do not want to change row 1 because I like that 1 that I have there. Negative 6 times 1 plus 6 is 0. Negative 6 times 1 plus 1 is negative 5. Negative 6 times negative 3 is 18, plus 1 is 19. Negative 6 times 4 is negative 24, plus 8 is negative 16. If you need to write these out, I find myself just kind of using my pencil or my finger to sort of follow along and do the calculations. I also want to do 5 times row 1 plus row 3 and put it in row 3 to get my 0 here. 5 times 1 plus negative 5 is 0. 5 times 1 plus 0 is 5. 5 times negative 3 is negative 15 plus negative 8. So wait, hold on. Negative 15, sorry, plus negative 4. Negative 15 plus negative 4 would be negative 19. 5 times row 1 is 20 plus 2 is 18. Okay. Typically my next step would be to get a 1 in this spot where the negative 5 is. But that's going to give me some yucky fractions. So I'd rather try to make this a little prettier first. And I notice that these are opposites. So I'm going to add row 2 and row 3. And put it in row 2. Actually doesn't really matter, but copy this down because I'm not changing it right now. I may end up switching these equations because I really want a 0 down here, and that's what I'm going to get. 0 plus 0 is 0. Negative 5 plus 5 is 0. 19 plus negative 19 is 0. Negative 16 plus 18 is 2. Well, that is interesting. That gives me 0 equals 2. Clearly, 0 is not 2 in our number system. So we have a contradiction there. We have no solution. Or we could say we have an inconsistent system of equations here. This is not possible. There are no x, y, and z that will make these 3 equations true. I did want to look graphically at what is happening in these situations. In Chapter 5, or Unit 5, we saw that if you have one solution, they intersect at that one point, right? That is your one solution. Parallel lines have no solution. That would be considered an inconsistent system. This one is consistent because it has a solution. It's independent because you don't have an infinite number of solutions. This situation, where they're the same line, they're right on top of one another, consistent because it has solutions, but it's dependent. In 3 variables, this is a little fuzzy. Sorry, that's a little fuzzy. It was the best I could make that image, and I thought it was a great image, so I stole it. In 3 variables, we have a similar situation, but with 3 variables, you don't have lines, you have planes. When you have one solution, that happens when those 3 planes, this green, this blue, and this peachish color here, intersect at one spot. Infinitely many solutions can occur in really a couple of ways. No, sorry, infinitely many solutions are going to occur when these 3 planes intersect at a line. So all of the points on that line are solutions. I guess technically it could also occur that you have infinitely many solutions when all 3 planes are identical. So they just lie right on top of one another. No solutions occurs in these 3 scenarios. The first one here is kind of like the parallel lines, where the planes themselves are parallel. So they will never intersect, so you will never find one point or any points that are true for on all of those planes. This picture in the middle shows that you have an intersection between the green and the blue, and between the green and the peach, but if the blue and the peach don't intersect at that same spot, you don't have anything that satisfies all 3 equations. Or here, that is kind of a similar scenario here. They don't intersect all at the same spot, so there's no solution. You need all 3 to intersect at the same spot, like here, or in this case, along a line, to have a solution. We are going to look here at how we find what's called a general solution in these scenarios. If we want a unique solution to a system of equations, meaning a single value for x, a single value for y, a single value for z, or however many variables you have, you must have as many equations as you have variables. If you have 2 equations, you need 2 variables. Otherwise, if you just have one equation with 2 variables, you have a line. There's not a single solution to that, right? Every point on that line is a solution. Same thing as you get into more variables. 3 variables requires 3 equations to be able to find a unique solution. It doesn't guarantee a unique solution, but if you have less than 3 equations, you definitely are not getting a unique solution. Like this. This has 3 variables, x, y, and z. It will not have a unique solution because you only have 2 equations. That does not mean that we can't find some information out about it, though. We can still write the augmented matrix here. It just will only have 2 rows. Still represents the x column, the y column, and the z column, and the constants. Let's try to do that Gauss-Jordan elimination on this and see what we get. I'll probably do 1/2 times row 1 and put it in row 1. It's not ideal because now I have to deal with some fractions, but I can handle it. I'm pretty sure we can do it. Let's copy the other equation over. We don't want to change that one right now. We want to change it in the next step, where I do 3 times row 1 plus row 2 and put it in row 2. Okay. I'm going to write these steps out just so everybody's clear because of my fractions I'm dealing with in some of these. 3 times row 1 is 1 plus negative 3. That gives me 0. This one is going to be 3 times row 1 is negative 7/2 plus row 2 is 4. That's going to be what? Negative 21/2 plus 8/2, negative 13/2. For this one, let's do 3 times 1/2 plus the negative 9. 3 times 1/2 plus negative 9 gives me 3/2 minus 18/2 is 15/2. Negative 15/2. And this one here, 3 times row 1 is 2 plus 1. That's 7. Okay. Next, I want a 1 where that negative 13/2 is. So let's do negative 2/13 times row 2 and put it in row 2. I want to use that reciprocal of that. When I'm getting the 1, I like to use the reciprocal unless the calculations are super yucky. These are not the greatest. But we just slow down and take our time and we can do it. 0, 1, 15/13, and 7 times negative 2/13 will be negative 14/13. Multiply by 7/1. Okay, now I want to get a 0 in that spot. I'm going to do 7/2 times row 2 plus row 1 and put it in row 1. Not changing the bottom row. So copy it over. 7/2 times 0 plus 1 is 1. 7/2 times 1 plus negative 7/2 is 0. This one I am definitely going to have to write out. 7/2 times 15/13 plus 1/2. Oy, oy, oy. Okay, 7 times 15 would be 105/26. I'm going to write that as 52/26. Who wrote this problem? I should have definitely picked something, but that's not right. 52, it's 13. Should have definitely picked something with nicer numbers than this. All right, 1/2, 13/6. Okay, so that's 118/26. That doesn't happen to simplify, does it? Let me check. They're both even, so it's definitely going to simplify there, but nope. It's a yucky decimal when I throw that in my calculator. But I can divide it both of them by 2. And that is 59/13. Geesh, who wrote this problem? Goodness. Okay, last calculation, I promise. 7/2 times row 2 is negative 14/13 plus 2. Negative, what is that, 28 and 70. Negative 98/26 plus 52/26 gives me negative, what, 46? over 26. Both are even, so we can go negative 23 over 13. I feel like I must have made a mistake on this. So real quickly before we get to the calculation, or what the interpretation of this, I'm going to go to my calculator and enter this matrix in and just make sure. I'm going to do a quick RREF, that reduced row echelon form, to make sure that my calculations were all correct. This is where if we were in class, you would all be screaming at me saying, no, wait, your calculation is wrong, if indeed it is wrong. It might not be. Let's take a look. Let's go to the graphing calculator. Clear that out. And clear this so you can follow along with the steps here if you want to. Go to the matrix. Oopsie. That's not what I wanted. Go to the matrix, second in matrix. Over to edit to actually change the matrix. This particular one is 2 rows because we had 2 equations, but it's still 4 columns. 2, negative 7. Be careful here that you're entering in the negative and not the minus sign. Negative 3, 4, negative 9, and 1. Okay, second and quit kind of saves that matrix. Back into the matrix menu, over to math, down to RREF, reduced row echelon form. Back into the matrix menu to grab the matrix that you want. In this case, it's matrix A. And hit enter. Yeah, that's yucky, which is actually good because I'm pretty sure, we'll see. What I want to do is I want to convert those to fractions. So go math and then fraction. See if it'll give me the fractions. I think that's what we got, isn't it? 59 over 13, 15 over 13. Negative 23 over 13 and negative 14 over 13. Let's go back. Ooh, 59 over 13. Yep, that's what we got. Okay, we did our calculations right. I just picked a really nasty problem. Sorry. Let's talk about what this means. We know that we cannot have a unique solution. We cannot get x equals a number, y equals a number, z equals a number. We can get x plus 59 over 13 z equals negative 23 over 13, and y plus 15 over 13z equals negative 14 over 13, converting those rows back to their equations. That first one here tells me that x equals, let me get rid of this stuff. We did those calculations. You can go back in the video if you need to see them still. Get rid of these, give myself some space here. X equals negative 59 over 13z minus 23 over 13 is what x would be if I solve for x by subtracting that z term from both sides. Here I get y equals negative 15 over 13z minus 14 over 13. What that tells me, if I want to write this as an ordered triple, is that z can be anything, and whatever z is, whatever number I pick for z, x is going to be negative 59 over 13z minus 23 over 13. And y is going to be negative 15 over 13z minus 14 over 13. We call this the general solution because we can find We have infinitely many solutions here. Z can be anything. You can pick whatever you want. Z could be 1,000,000, and you can find X and Y based on that because they are written now in terms of Z. That's my general solution in this dependent system. Finding two particular solutions just means you plug in a number here. So let's go here. I might say let Z equal 1. I don't know. Then X will equal -59/13 times 1 minus 23/13. -59/13 minus 23/13. Their common denominator already, right? So -59 minus 23. My brain is tired tonight. -82/13. And Y would be -15/13 times 1 minus 14/13, or -29/13. So one particular solution would be -82/13 for the X, -29/13, Z being 1. That's one solution. You could do the exact same thing, picking a different value of Z and running the calculations. This video is getting a little long, so I'm going to stop there and not do a second one, but I hope you can see how you would. You would just pick a different number for Z, use it in place of the Z in this X and Y. Okay, that's a lot with the independent versus dependent solutions, consistent versus inconsistent solutions. So take some time with this and think about what's really happening here and how you get to each of these scenarios, because that's what we are working on in this situation, is those sort of strange situations where you do not get a unique solution.